My name is Jacob Schweenard. I'm a mechatronics engineering student at the University of Waterloo in Waterloo, Ontario. Today we're going to be talking about this curvature-based Raceline optimization project that was completed as part of MathWorks Excellence and Innovation program. The link to the GitHub is nearby. Do not worry. With that, let's take a better look. So before looking at the solution, of course, we should get a better understanding of the problem itself that we're trying to solve. So to do that, I'll go ahead and pull up the GitHub for this Excellence and Innovation project, and we'll go from there. Okay, so here we are. This is the MathWorks Excellence and Innovation project repository for path planning for autonomous race cars. This is project number 208. And the entire focus of this project is essentially, given an arbitrary track, we should be able to take the race line that an autonomous car would follow and optimize that either for performance or curvature. Curvature does improve performance as compared to shortest path performance. However, it's not necessarily the best performance, as curvature and performance don't have a one-to-one correlation. So of course, there's additional description about the project itself, some suggested steps, as well as very, very useful background information. Yeah, with that said, let's go ahead and start taking a look at the solution. Now that we've got a better understanding of the problem, we can go ahead and dive into the solution. In summary, my solution for the problem relies on discrete mathematics and an iterative pattern search optimization technique to create a race line that is now optimized for curvature. The GIF on the right side of the screen actually shows this process of optimization. Each point is optimized based on the 2 points before and 2 points after it that will impact its curvature when it's all converted into a spline. For ease of calculations, each point is constrained to a radial chord, which are the multicolored lines you can see on the GIF. The position of each point is also constrained by the track width as well as the buffer regions. This prevents the calculated race line from intersecting the track boundaries. Once optimization is complete, our velocity profiling begins. Based on maximum normal and tangential forces established by the user, we use a simplified point mass model to simulate going around the track for a user-specified number of laps. The best lap is taken and plotted as a velocity gradient on the track, which is what you see in the bottom right. There are also several other types of visualizations available, which include PNGs of the optimized track, videos of the mass going along the track in real time, videos of the path optimization process, as well as a PNG plot of the velocity profile with respect to distance traveled along the track. So now we have a solution methodology map, which essentially lays out how the program itself flows. So to start with, we look at OpenStreetMap data. OpenStreetMap data allows you to take any section of road and convert it into something that's readable by the program, and it's very useful. This data is saved as a .osm file and can be imported directly into the driving scenario designer. So the driving scenario designer processes this road information based on user instruction and will help us generate our track data. This will be saved as a .mat file and can be exported as a .m file so that it can be read by your program later on. So moving on to the bulk section of the code, let's go ahead and start at the curvature LiveScript file. LiveScript file allows for user input to configure the optimization and velocity profiling, as well as the graphical outputs they want. We'll go through this in detail a little bit later, but in short, LiveScript will import the .m track files and parse the data to create a set of points that represent road boundaries and the center line. The center line, as well as the user-defined optimization parameters, are then passed to the discrete waypoint optimizer file. So we've discussed how the optimization process worked in the previous slide, and we'll touch on it again in the next one as well. The optimizer will return an acceptably curvature optimized raceline, as well as a set of data that exists for graphical outputs based on what the user wants. The optimized raceline and user-defined velocity simulation parameters will be passed into the velocity profiler function as well. The velocity profile identifies the maximum velocities at instantaneous points on the track, generates a set of velocity profiles by identifying local minimum critical velocities based on the physical constraints of our point mass simulation. The minimum of all these profiles are assembled to form our velocity output data. This output data, as well as another set of data for graphical outputs, will be returned to the live script. At this point, the live script will determine whether or not to pursue different graphical outputs based on the user input. These graphical outputs are detailed a little bit later, but the functions are writer1, writer2, writer3, if writer. Once these outputs are complete, the live script will by default export two default PNGs. One is the velocity gradient of the best lap, which we saw in the previous slide, and the other one is the velocity profile as a function of distance traveled along the path. And now that we've covered the high-level stuff and a bit of the nitty-gritty, we can go ahead and take a closer look at the optimizer. So within our optimizer, the local optim function is responsible for shifting the points of the track in pursuit of curvature optimization. For each point, the optim function looks at the previous two and the future two. The set of 5 points is rotated and centered at 0, 0, such that our radial chord that we're optimizing along is aligned with the y-axis. This takes a two-dimensional problem and turns it into a one-dimensional problem. The pattern search optimization is then called and is used to optimize the chordal position of the point that we're looking at. In this case, it's P. Then its position then becomes P prime, and all of the points are returned, and its position is updated with respect to the grand scheme of the Raceline. Moving on, let's go ahead and take a look at the live script, as well as a quick demonstration of how this all works. Okay, so here we are in our MATLAB development environment with our live script pulled up. If you've never used it before, the driving scenario designer that we'll be using is located in the apps panel. It's right here. Already got one pulled up. Let's go ahead and take a look at that. This is the driving scenario information for the oblong track that is found in the GitHub repository. So once we've either created our own track or we have imported one through OpenStreetMap data, we can export it as a .m file. Now this .m file is what we'll actually be using later on, and it's what we can access information from in a meaningful way. So closing down that, we have just our general overview here, but first let's go ahead and take a look at the discrete waypoint optimizer. We talked a little bit previously about what it actually does, but here we have a high-level summary that it optimizes input waypoints for curvature using iterative pattern search algorithms. We have descriptively our inputs, and equally descriptively, we have all of our outputs. And so all of this is fairly well documented in the GitHub repository. If you want a more specific understanding of how it works, I highly recommend that you take a look at it. There's a lot here to cover, and I don't necessarily think that going through every line one by one is the best use of our time. But as a high level, it goes through every point along the lap, optimizes it with respect to the points ahead of it and behind it, as we talked about. And once we reach a certain threshold, the loop breaks and we return back to our live script. Going from this, let's go ahead and take a look at our velocity profiler. We haven't talked on exactly how this one works a lot. The logic behind it is found in this research article here by Tyler Friedel. That is essentially the research that this model is based on. It's a very interesting read. I highly recommend it. Similarly, we have our inputs detailed here and our outputs detailed here. And essentially what we do is we look at minimum critical velocities in certain instantaneous areas and build profiles off of those. So if you have a graph, you find your minimum, and then we start building in either direction. And we do this for every critical minimum that we can find. And we take them all, put them next to each other, and take the minimums across the board. And that's what generates our minimum, or that's what generates our velocity profile. Since this is, of course, a simplified point mass simulation, it's not going to be as accurate as, say, a high-fidelity dynamics model. It could definitely be improved through the implementation of a dynamics model, and that may be in the future of this project, but it remains to be seen. So going back to our live script, so some key elements here. This all has to do with the administrative stuff of the script. Right here is our first user input. We can go ahead and select any of our tracks. For this one, let's go ahead and use our oblong track like we showed earlier in the driving scenario designer. This is our video outputs. For the sake of processing time, I'm going to leave all of those blank. So here's where we have the importation of our driving scenario information. Here's where we have the importation of the driving scenario information. The driving scenario information is then extracted by looking at road boundary properties of driving scenarios. These road boundaries are then compiled in a way that's meaningful and assembled so that we can actually determine them properly. It's where we get our outer bounds and our inner bounds, as well as our initial line, which is our center line. So as we start passing things into our optimizer, what happens is that they're normalized. This essentially means that rather than our track being of length 208.127589 meters, we use a normalization factor such that it becomes 209 meters. And this is so that our initial center line can be more easily generated because it can be equally spaced the entire way around the track through increments of 1 meter. And that really helps us build our initial settings. So we normalize our inner and outer bounds as well as our initial center line, and we pass that on all of that. In addition to the user-specified optimization parameters into the discrete waypoint optimizer that we talked about previously. We have maximum iterations, minimum change in curvature, the maximum allowable rise in curvature, because it does happen that while we're minimizing every instantaneous point, it won't necessarily reduce the overall curvature, but if you let it run long enough and give a sufficient rise allowance, it will continue to drop. We also have our buffer size, in which case is specified here to be about 20% of the track's width. Video set values here are for the video outputs, depending on what the user selects. And so once that returns our optimized waypoints, as well as the video sets, we can then move down to our velocity profiler, where we have an established time step, which is 1 millisecond. We have an established lap quantity, here's 3, our maximum force in terms of newtons, our maximum normal force in terms of newtons, maximum velocity, and the mass of the vehicle, in this case 300 kilograms. All of these are passed into the velocity profiler, and it returns a velocity profile as well as a velocity profile with respect to distance rather than time. We then select our minimum time lap, which will be the middlemost lap, and we use that to generate our PNG of the velocity gradient. At this point, we also extract the total number of iterations and the ending curvature of our path so that we can display it on the PNGs and the plots at the end of the script. So here are the things that check the user inputs to determine whether or not to call graphical output. Here are the default outputs, which is the best lap velocity curvature optimization, and that's the gradient that we saw previously. And this one outputs the velocity profile as a function of distance. And here are the further output ones. I won't go into the nitty-gritty with those, but they're fairly standard. Select frame from a plot, store it, and output it. So now that we have all this established, let's go ahead and use our oblong with 5 maximum iterations and the values that we saw previously. Let's go ahead and take all of that and let's run it. Now, of course, it does take a minute because the discrete approach requires calculations for every point along the track. And even though we're only doing maximum 5 iterations, it still does take time. So you can see down here, we're already on iteration 4. Iteration 5 completed 21 seconds. Not bad. When you're going through perhaps 30 or so iterations, you're looking at 120 seconds, so 2 minutes or so. Velocity profiling took 2.62 seconds, so not a significant amount of time. And then we have our outputted gradient and our outputted velocity profile. And now these are two very different graphs, but they do represent essentially the same thing. This is our best lap velocity, and this is all the laps velocity. So best lap would likely be somewhere in between here and here. And you can see in total, for 5 iterations on the oblong track, it took about 38 seconds to complete. Now, I did mention previously that the best place to look through documentation is in the GitHub repository for this project. In my opinion, there's no better documentation for it than the documentation created by the person who made it. Yeah. There's definitely some example outputs, example GIF outputs. There's 3 tracks total that are in the repository with it, which are the oblong, the kidney bean, and actually the Silverstone testing track, which is an F1 track out of the UK. I'll be sure to link this wherever I can. And yeah, if you want more information, definitely check it out. Okay, and now that we are back from our live demonstration, I do want to touch a little bit on some of the limitations of the model. A big issue is that we're not looking at continuous math. We're looking at discrete mathematics, which is each point as itself. So it's not necessarily as precise as exact for a continuous model, which has every point on the track rather than only a set number of points on the track. We're also looking at linear approximations between lines. So that does mean that there's a possibility that even with the buffer region, that if we don't have a high enough resolution path, or we have too few points, that these lines are going to intersect track boundaries. And that's why we have the need for the buffer zone in the first place. Looking at the point mass simulation, it's a simplified point mass simulation based on kinematics, so of course it's not as accurate as dynamics. I touched on that earlier, but it is worth pointing out again. The limitation is scalability. Looking at execution times between the example oblong track versus the Silverstone track, where oblong is maybe 150 meters long, Silverstone is a significantly longer course that has a significantly more complex geometry. So it does take a lot longer to complete. 3-lap simulation of Silverstone could take between 10 and 20 minutes, whereas oblong, if we do enough optimization iterations, can take about 1 to 2 minutes. All that being said, I do want to give a big shout out to the Excellence and Innovation program by MathWorks. It's been a very positive experience. I've enjoyed a lot of it. I learned a lot of things I didn't know previously. It was a very useful way to get exposed to a lot of different commands and functionalities that MATLAB has that I didn't necessarily use previously, like our visual outputs, our videos, our GIFs, our PNGs. You get to interact with MathWorks engineers, and they're very helpful as well. It's also a fairly collaborative process. There's a lot of people sharing resources in some of these projects. Over the course of working on this, I read 5 to 10 different research articles all about this same sort of thing. If you've never looked into this sort of excellence and innovation repository or project before, definitely look into it. There's a lot of different projects that rely on different softwares, different toolboxes, different types of problem solving. This one was very mathematics oriented, but there are ones that are predictive analytics, machine learning, that sort of thing. With all that said, I'll be wrapping this up. I hope you enjoyed learning a little bit about this project. I know it's a little dense, but go ahead and take a look at the GitHub repository, read some of the documentation. If you have any suggestions, feel free to send them my way. And if you're a student, anywhere here, anywhere there, definitely take a look at excellence and innovation. Yeah, that's about it. Cheers, everyone.